Okay guys, we are going to wrap up our discussion on Gibbs free energy. So just remember from the last video that delta G, or Gibbs free energy, is ultimately what decides whether a reaction is thermodynamically favored or not. Just remember that that negative sign on delta G indicates that it is thermodynamically favored. That also then indicates that the reaction will be product favored. It's going to proceed ultimately to the products. And the reason why that's important is that our final equation involves the equilibrium constant. So we know, just going back to equilibrium, that a K value greater than 1 means that it's product favored. So if we have a negative delta G, which is thermodynamically favorable, we would expect K to be greater than 1, meaning that the products are favored. Or if we find that delta G is thermodynamically unfavorable, that you have a positive delta G, then we would expect K to be incredibly small, meaning that it's very heavily reaction favored. So just keep that in mind kind of going forward, especially when you get to the practice. So we're going to start with exercise 7. It gives us a balanced equation. It's asking for the equilibrium constant, and we're given delta H and delta S, or sorry, just S. So when we go to calculate this, we first have to find delta G, and then once we find delta G, we can find the equilibrium constant. I think the hardest part for students is just keeping track of units with this, so just make sure you're really paying attention to it. So for delta H and S, when we go to find delta S, just keep in mind we're going to be doing products minus reactants. I'm going to save us a little bit of time in the video and just give you the final values for delta H and delta S for the reaction. So you might want to just pause and just double check for yourself, make sure you're okay with each of these. You should get for delta H an exothermic reaction, so 1,652 kilojoules per mole of your reaction. And for delta S, you're going to end up getting negative 593 joules per Kelvin times mole of the reaction, which makes sense that entropy is actually decreasing. You're going from a solid and a gas and 7 particles to just a solid. So that makes sense. We have an exothermic reaction in which entropy is decreasing. So this is where we have a favorable enthalpy change, but an unfavorable entropy change. Now, one thing in order to calculate delta G is with these values being different units, I'm going to convert my entropy value to kilojoules, because usually Gibbs free energy, we look at it in terms of kilojoules. So this would be 0.93 kilojoules per mole of the reaction times Kelvin. Okay, then from there we're going to use the formula that we went over in the last video. So we're going to use delta G is equal to delta H minus T delta S. We're going to plug in our delta H, so negative 1,652 kilojoules per mole of the reaction, minus temperature was 25, so plus 273, you're going to have 298 Kelvin, times our entropy, so negative 0.593 kilojoules per mole of the reaction Kelvin. All right, and then when we get delta G there, we get negative 1490, so negative 1,490 kilojoules per mole of the reaction. So this is showing us that it is thermodynamically favorable. Remember that negative value for delta G, which means when I go to calculate my equilibrium constant, I should be greater than 1. So for delta G, I'm going to use negative RT ln of K. So I'm going to initially plug this in, so negative 1490 kilojoules per mole of our reaction. Okay, this is going to equal negative, my R value is 8.314 joules per mole Kelvin. Temperature is 298 Kelvin, and then we'll have the ln of K. So one thing you have to be careful of is now, I usually don't like to switch the constant, so I'm going to take delta G and switch it to joules to match up with the universal gas constant. So that I would actually have to multiply by 1,000, so you get here negative 1.49 joules per mole of the reaction, I should have a 0 there, divided by that negative 8.314 joules per mole of the reaction, or sorry, mole Kelvin, times 298 Kelvin, which would give us the ln of K. So then you would take like the whole natural log, and when you actually get K by itself, and you would have like E raised to this expression, and it's a huge number. So when you actually get your equilibrium constant, for me, I get an overflow result in my calculator, which means it's obviously a massive number, which you can tell by the answer key there, that it is. So that supports the fact that this is thermodynamically favorable, and it is heavily product favored. Basically, you would almost assume that it goes to completion in terms of the reaction. So just to kind of show you how that equation works. This next example that the NIMSY packet has to do with actually phase change. So this is kind of switching gears. And this little part here actually goes with exercise 8. So it says the Gibbs equation can also be used to calculate the phase change temperature of a substance. During that phase change, the system is at equilibrium, thus the value of delta G is 0. So I'll just go through this one with you as well so that you've seen it. So here, calculate the thermodynamic boiling point. So we're going to be looking for temperature of the vaporization of water given this information. So again, just being careful with units. And then just so you have it over here, this is when you're going to use it for, when determining temperature, you're going to set it to delta G is equal to 0. And again, this is going to usually occur when we talk about phase changes, like in this example. All right, so we're going to go ahead, we're going to say delta G is equal to 0, and that is going to be equal to delta H minus T delta S. And you can see those little knots are gone because we're not at us like standard conditions in this case. We're looking for temperature. So some of you guys might notice that. So when we rearrange this for T, we're going to see that we get delta H divided by delta S. So I'm going to plug these values in. So I'm going to use my 44 kilojoules per mole of the reaction, which is positive endothermic. Delta H or delta S, I'm going to divide by 1,000 when I go to plug this in. So I don't know why I'm making that negative. So 0.1188 kilojoules per Kelvin mole of the reaction. And when you get this, you would get 370 Kelvin. Okay, and they're just using the 2 sig figs there from delta H. And that would be your temperature. That those conditions would be present. All right, for this last exercise number 9, we are given delta G, and then we are going to calculate that equilibrium constant K. So we're going to use the same expression or equation as we were using in exercise 9. So we have negative RT ln of K. I'm just going to initially arrange this for ln of K, so that will be our delta G over negative RT. So I can plug in my negative. Now I'm going to change this to joules. So I'm going to multiply by 1,000. So negative 2.572 times 10 to the 5th joules per mole of the reaction divided by negative, and then R here is 8.314, which is the value that's actually given on the reference table, which is a little bit different than the one that's on the NIMSY packet, just so you're aware, times Kelvin times 298 Kelvin. So when I rearrange this, I get K is equal to E, and this will end up being like rounded to 104. I use the value in my calculator, so when I actually get this, I get again an overflow amount again, which then would relate to this large value, which makes sense. I have a negative delta G, that means it's thermodynamically favorable. I would expect it to be product favored then, so this really large K value supports that. Don't worry about this little piece here where you have the E cell. We're not getting into that part of our redox unit, so we can kind of skip that piece here. But they're just kind of giving you an overview, relationships of delta G to K. So again, especially this negative and positive value here, when it's equal to 0, it's at equilibrium, so we'd expect, it says K is equal to 1, but not necessarily, because it could be either or there in terms of product or reaction favor, so just be careful with how you understand that piece of it. However, if delta G is negative, we would expect K to be greater than 1 to show it's product favored. If delta G is positive, we would expect K to be less than 1. And this part, we won't really get into too much this year with it, but it's basically saying if delta G is positive and it's not thermodynamically favorable, it doesn't mean that it can never occur. It's just we have to use outside energy to drive those changes. So sometimes this will get into like coupling. So you'll take a favorable reaction and couple it with that unfavorable reaction in order to help it using electric current, which we would get into if we were doing the rest of our redox unit and that type of thing. So just something to just be aware of. All right, we are all set.